A twin-boom layout in aviation is a true exotic. The arrangement has its advantages. For reconnaissance aircraft, it provides excellent visibility and a wide firing sector. At the same time, engineers must solve a number of specific problems. For example, a complex interaction of airflow appears between the tail booms, the wing, and the tailplane, which negatively affects the aircraft's handling. Drag increases because the air flows around a larger surface area. Questions of overall structural strength arise, the control system and other assemblies become more complicated. These are only part of the difficulties faced by the designers of the experimental reconnaissance aircraft Praga E51. This airplane appeared in the troubled period at the end of pre-Munich Czechoslovakia, and known historical events prevented it from taking up the defense of its country. Nevertheless, it occupies a worthy place in the history of Czechoslovak aviation, not only because of its originality, but also as an example of how dramatic the paths of technical progress can be. It is interesting that such a bold project was implemented by the comparatively young aviation division of the ČKD-Praga concern, which was founded in 1930. It gained renown in aviation circles primarily thanks to the sport plane E-114 Air Baby. Other Praga types also served in the Czechoslovak Air Force, for example E-39, E-41, and E-241. Part of their production was taken over by the Letov company, with which ČKD-Praga concluded a contract. In the first half of the 1930s, Praga built for the military only experimental aircraft. The older firms, Letov, Aero, and Avia, firmly held their positions as suppliers of equipment for the Air Force, and it was not easy for newcomers to displace them. The originality of some technical solutions by the chief designer Jaroslav Šlechta did not help either. After the departure of the well-known designers Pavel Beneš and Miroslav Hain, Šlechta became the soul of the aviation division and the inspirer of all its developments. The experimental fighter E-45, sport planes E-114, E-214, E-115, and E-117, the transport E-210 with pusher propellers, the trainer E-40, and finally the E-51. Šlechta became interested in the twin boom scheme, he himself called it twin fuselage, around 1936. This interest materialized in projects for the bomber E-48, the light fighter E-52, and the reconnaissance observation aircraft E-51. Only the last of these was realized, and that only after the appearance in November 1936 at the Paris Air Show of a similarly configured airplane, the Fokker GI helped overcome the skepticism of officials at the Ministry of National Defense. The impetus for the development of the E-51 was the experimental aircraft program compiled by the aviation section of the Ministry of National Defense in January 1936. The modernization program for the Czechoslovak Air Force envisaged the creation of 4 types of aircraft: Type 1, single-seat fighter; Type 2, two-seat fighter bomber; Type 3, three-seat day and night reconnaissance aircraft, observation plane; and Type 4, multi-crew day and night bomber. Initially, a commission of 40 specialists conducted a survey in operational Air Force units and then visited the aforementioned Paris Air Show. Only after this were concrete tasks issued to the firms. Type 2 was eventually excluded from the program, while work on Type 3 produced the Letov Š-50 and the Praga E51. Thus, the E51 was a 3-seat reconnaissance aircraft. In its central nacelle, the pilot was seated on the left. The observer, who was also the photographer and bombardier, occupied a glazed nose section, and in the rear of the nacelle there was a glazed gunner's cockpit with a machine gun. Thanks to the placement of the fins on the ends of the tail booms, the gunner had an unobstructed view and field of fire to the rear hemisphere. The proposed concept fully met Type 3 according to the Ministry of National Defense requirements of May and June 1936. Among the general requirements for the aircraft were predominant use of domestic materials and compliance with national standards. The structure had to be simple and rational. The airframe service life was set at 300 flying hours or 2 years of operation without major overhaul. The specification called for fabric covering. The empty weight of the aircraft was to be about 8,700 pounds. An excess of up to 10% was allowed. Maximum speed at 4,900 feet. Not less than 186 miles per hour, time to climb to 9,800 feet. No more than 10 minutes, landing speed, not above 56 miles per hour. In the preliminary technical conditions, the military undertook to equip the aircraft with bomb racks, gun mounts with machine guns, oxygen equipment, photographic equipment, and some instruments. Everything else was the firm's responsibility. The prototype was to be delivered to the military fully equipped after passing strength tests at the Military Technical Aviation Institute. There were several variants of the E51 project, differing mainly in the outlines of the central nacelle. In the initial version, the forward glazing was more protruding and angular, and in the rear of the nacelle, it was planned to install an Armstrong-Whitworth gun turret, which was produced under license by the Tatra Company. Various variants were tested as models in the wind tunnel of the Military Technical Aviation Institute, and the convenience of their layout was evaluated using full-scale nacelle mock-ups. Structurally, these were a wooden framework covered with paper or fabric. For the power plant, it was initially planned to use Praga FR engines of 620 horsepower, Avia RK-17, 360 horsepower, and in the end, the choice fell on Walter Sajida engines rated at 550-600 horsepower. The wing of the prototype, whose construction was completed in the winter of 1937-1938 at the Praga factory in the Karlín district, consisted of 3 parts. The middle section, rectangular in shape, ended near the tail booms. Oval-shaped consoles were attached to them on the outside. To remove the large structure, which consisted of the central cabin, the central part of the wing, and the tail booms, from the workshop, the gates had to be widened. For this, a wall was even broken through. The final assembly of the aircraft was already carried out in the company's hangar at the Letňany airfield, not far from the Letov factory. It was delivered there on May 20, 1938. We can learn about the progress of the tests and preparations from the preserved notes of the test pilot. For some reason, his name is not mentioned in the article. Essentially, he was the only judge of the flight characteristics of the new machine, since sensors and recording equipment in the modern sense practically did not exist yet, and the testing methodology was also not developed. First, the aircraft was carefully inspected, weighed, the deflection angles of the control surfaces were measured, and minor defects that needed to be fixed were noted. In particular, there were no rubber steps on the wing, the handle above the pilot interfered with moving the seat adjustment lever, the fire extinguisher mount needed reinforcement. The landing flap control lever had to be modified, and finally the color indication of the flap deflection angle and the level mark needed to be made clearer. Most of the improvements were completed by May 27th. Meanwhile, on May 26th, after completing engine tests, the aircraft made its first ground run. After approximately 10 runs at gradually increasing speed, the following conclusions were drawn. Vibrations in the controls were minor, but with the engines running at a constant regime, it was impossible to keep the aircraft on course using the rudders. It was necessary to work with brakes or engines. On uneven surfaces, the landing gear suspension was good, the damping was stiff, and the tail section vibrated strongly in the transverse plane. During taxiing at high speed, the aircraft pulled heavily to the right. It was difficult to lift the tail and the brakes were ineffective. On the same day, May 26, 1938, at 18 hours 29 minutes, the aircraft made its first 6-minute flight. According to the pilot's assessment, the aircraft was tail-heavy. The effectiveness of the ailerons was good, but the rudders were insufficient. The action of the elevator trim tab turned out to be the opposite of what was expected. Once again, vibrations of the tail section appeared. The landing flap control lever was installed in such a way that the pilot could not reach it. In addition, a wrongly installed sliding window of the cockpit was lost. During taxiing on May 28th, the left engine stalled due to a broken fuel pump. 2 subsequent flights took place on May 30th after increasing the elevator trim tab. The aircraft could be balanced along all 3 axes, but as speed increased, the intensity of vibrations grew, and they were clearly felt in the controls. When landing with flaps deflected at 25 degrees, the landing gear felt too stiff. Vibrations in the tail section were explained by disturbed aerodynamics caused by the machine gun turret, which protruded significantly from the fuselage. The turret was removed, and the opening was covered with fabric. Test flights on the last day of May showed that vibrations no longer increased with rising speed, but it was not possible to completely eliminate them. Visually, the tail section of the aircraft no longer vibrated, but trembling was felt in the rear part of the nacelle and was transmitted to the elevator and aileron controls. The upper cowlings of the engines rose by themselves in flight by approximately 0.4 inches. Therefore, before the next flight, the outer parts of the cowlings were removed, and at the same time the cylinder temperature was measured. It decreased by an average of 15 degrees. Insufficient cooling and other engine-related problems were generally resolved during the course of testing. On May 31st, 2 more flights were carried out with extreme positions of the center of gravity. On June 2nd, the company's test pilot and an aerodynamics specialist performed a flight during which cotton threads were attached to the rear part of the aircraft to visualize the airflow. Engineer Schleta recalls, "All efforts were aimed at determining the cause of the vibrations that constantly accompanied the test flights. We looked for it in the unfavorable airflow around the rear part. That is why the Armstrong machine gun turret was removed. The engines were examined, the control system, in particular the elevator, was modified and reinforced. These problems, as well as the nose heaviness when recovering from a dive, were the only reasons for all the modifications made." Starting from June 7th, flights were conducted with new oil cooling radiators. The rear outlet slot of the engine cowlings was widened, and the cowlings themselves were lengthened. On June 8th, tests were conducted to see how stable the aircraft was in flight with forward center of gravity. It was confirmed that at high speeds, the aircraft was insufficiently stable. Already the next day, the size of the horizontal stabilizer was increased, but the next 2 flights did not show any improvements. On the following flight day, the airflow movement with the engine cowlings removed was studied with the help of special threads, and experiments were carried out with installing and modifying ducts to the exhaust pipes. On June 15th, enlarged fairings between the rear part of the nacelle and the wing were tested. With their help, it was hoped to eliminate airflow vortices in this area, but this goal was not achieved. Moreover, the effectiveness of the landing flaps decreased significantly. When only the outer sections of the flaps were deflected, the aircraft nodded nose down, and when all the flaps were extended, tail down. Therefore, the inner flaps were temporarily disconnected. After installing the new oil radiators by Fiedler and modifying the cowling of the right engine, the measurements taken on June 27th showed that, contrary to expectations, the oil began to heat up even more. Therefore, on June 23rd, most likely meaning June 28th, for one flight, the side covers of the cowlings were again removed. At the same time, the intersections of the flaps were reconnected. The next day, the rear part of the nacelle was redesigned, giving it the shape of a vertical fin. This reduced vibrations. The remaining vibration was linked to the elevator. Therefore, the hydraulic damper in the longitudinal control system was replaced with a friction damper. However, it was set to such a strong resistance that during flight, with the control stick released, the rudder could stably remain in any position. At the same time, vibrations at high speeds remained unchanged, as shown by the flight on June 29th. When the outer sections of the flaps were disengaged, a pronounced tail heaviness appeared. The hydraulic elevator damper was then reinstalled, and an asymmetric stabilizer profile was also tested, but with it, the aircraft became even more unstable. After landing, it was discovered that the attachment of the tail booms to the wing was not rigid enough. A noticeable shift of the metal panels could be seen, which could have contributed to the vibrations. On July 2nd and 4th, modifications of the deflectors on the middle cylinders of the engines were carried out, but it was still impossible to achieve sufficiently uniform cooling. The first stage of testing ended on July 13, 1938, when the prototype, along with the Aero A300 and Avia B-158 bombers, was demonstrated to foreign guests at the Kabylie airfield. The next day, it was dismantled and transported to the factory, where extensive modifications and redesigns began, lasting until the end of the year. The most noticeable change was the new design of the rear gun position. The rear part of the nacelle now had the shape of a pointed spindle. The wing was made integral. Previously, there were joints on the outer side of the tail booms, which provided significant weight savings. The nacelles were lengthened and the engines were moved forward for balance reasons. At that time, the political situation in Europe was rapidly deteriorating. The betrayal of Czechoslovakia's Western allies and the local bourgeoisie led to the shameful Munich Agreement. The Republic was reduced. Nevertheless, work on the E51 continued. The aircraft's equipment was evaluated by a commission that gathered on January 13, 1939, at the ČKD factory in Karlín. It consisted of employees of the 2nd Department of VTLU and company representatives. Some deviations from the technical requirements were noted, which required improvements. It is worth describing them in more detail, as they provide an idea of the final configuration of the aircraft. The instrument panel was made as a single unit, although originally the navigation instruments were supposed to be placed on a separate panel. The entire panel was cushioned so that vibrations did not exceed the permissible plus-minus 0.004 of an inch. The connection of the navigation instruments directly to the vacuum pump was deemed satisfactory. Due to lack of space, the movable seat for the navigator in the nose was abandoned. Only a functional mock-up was made, mounted on wheels and able to move along special rails. The Commission demanded that this seat be replaced with a portable cushion, which would serve the navigator for seating next to the pilot during takeoff and landing. Due to the redesign of the rear gun position, the Commission pointed out insufficient glazing of the upper fuselage in this area and required 3 windows to be cut at the specified places. The modification of the rear turret itself was approved, primarily because the new version provided protection of the entire rear hemisphere, including from below. The gunner's entry hatch was moved to the upper left side of the nacelle. In the initial version with the Armstrong turret, it had been located underneath. Because the machine gun was mounted in a rotating installation, it was impossible to supply it with belt-fed ammunition. Drum magazines had to be used. The gun mount turned too heavily, so it was planned to manufacture a suitable handle. The mechanical trigger of the machine guns was rejected due to the high effort required, and the Commission demanded it be replaced with an electric one, as on the Praga E51. The bomb armament was deemed satisfactory, but the use of a smoke device was rejected due to the possible contamination of the aircraft itself by its chemical content. Regarding instrumentation, it was ordered that the pilot's compass be replaced with a special navigator's compass, installing it, as on the B-71, on the cabin floor in front of the drift indicator, which the company had also not installed at that point. The control of the trim tabs was too heavy. The Commission demanded that the lever for operating the landing flaps be redesigned so that its forward position corresponded to extended flaps. Fire extinguishing valves were to be painted red, and the fire cocks of the fuel system yellow. Instead of 2 lamps, only 1 was installed. After reconstruction, the E-51 was rolled out to the airfield again on February 1, 1939. A week later, it was weighed. The empty mass was about 6,800 pounds, 550 pounds less than the initial version. Some deficiencies in the control system were noted. For example, the control of the trim tabs still required excessive effort. At the very first engine start, it turned out that the hydraulic system of the left engine control was defective. It was impossible to shut down the engine normally. It was necessary to use the air shutter. At low revolutions, a metallic sound of the reduction gear was heard. On the right engine, the throttle lever operated in the reverse direction. The hydraulic pump of the landing flaps did not produce enough pressure for their full retraction. Leaks were also found in the rubber connections of the oil system pipelines. The first flight of the updated E-51 took place on February 11. During it, significant play was found in the engine control levers. The elevator trim tab did not work, making the aircraft tail heavy. Control was imprecise. In the lateral axis, the ailerons did not deflect to their full angle due to slack, and vibrations were still observed. In addition, the brakes were connected incorrectly. On February 14th, during climb rate testing, engine problems occurred. The left engine failed, and the pilot was forced to return to the airfield. The carburetor, magneto, and spark plugs were replaced. Experiments with ignition timing were carried out, but the engine continued to malfunction. After several subsequent flights, on February 23rd, the prototype was presented to the Bulgarian military mission together with the E-39, E-241, Letov Sh-50, and Praga E51 aircraft. That same day, the left engine was dismantled and sent to the Walter factory. It returned only a month later, on March 22nd. Meanwhile, on March 15th, Hitler's Germany occupied the remaining part of Czechoslovakia. The Germans seized the aircraft factories and production came to a halt. Thus, the program to create the E-51 for the Czechoslovak Air Force remained unfinished. At that time, the test pilot presented Chief Designer Schlechte with a final report, in which he assessed the lateral stability of the aircraft as very good, directional stability as good, but longitudinal stability as insufficient. Control forces on the ailerons were very high while their effectiveness was low. By contrast, the rudder worked excellently, and elevator control, though somewhat heavy, was still acceptable. This relatively promising feedback on the flight qualities of the E-51 served as confirmation to the designers and workers of Praga that they had chosen the right path. But it was already too late. The arrival of the Germans sealed the fate of the aircraft. It could no longer serve its homeland, and no one wanted to continue production for the new masters. On Friday, September 1st, 1939, Hitler attacked Poland. The Second World War had begun. When the Czechoslovak aircraft factories were taken over by the Germans, the German military administration ordered the continuation of E-51 testing. The Praga employees, however, had little desire to work for the Reich, so the work continued slowly and with interruptions. At first, modifications were made to the control system. The aerodynamic balance of the ailerons was increased, the trim control was redesigned to electric, the control column was reinforced, and so on. During a test flight on April 18th, with the left engine again malfunctioning, it was noted that the ailerons deflected easily and acted quite effectively. However, the vibrations did not disappear, and as before, increased with speed. Therefore, it was concluded that their cause was not connected with insufficient rigidity of the control system. At this point, the E-51 tests in the spring of 1939 were concluded. Testing resumed only at the end of July under pressure from the Aviation Institute, which was already under German leadership. The Germans demanded that the aircraft be transferred from the factory to the institute. Constant problems with the engines became a convenient reason to officially acknowledge that the initial order of the Czechoslovak Ministry of National Defense for the E-51 prototype would not be fulfilled by the set deadline of December 15, 1939. The aircraft testing continued very slowly, like everything else in the German-occupied Protectorate of Bohemia and Moravia. Another failure of the left engine forced the replacement of cylinder heads, but this also did not help. The governor of the right engine also had to be repaired. After another cylinder head replacement and repair of the hydraulic throttle control system, only one flight was made on October 17th. The next two flights took place only on November 6th and 7th. After them, it was decided to completely redesign the throttle control, since synchronizing the operation of both engines was practically impossible. Instead of the hydraulic drive and complex system of rods, a Teleflex metal system was installed. It worked very reliably, contrary to the pilot's initial doubts. Essentially, it was a steel cable running through light tubes made of magnesium alloy. The only problem was the high friction at sharp bends of the tubes. This was solved by replacing the bent sections with brass tubes. However, engine problems continued, and during the test flight on January 10, 1940, this time the right engine failed. Further modifications included replacing the left engine with a new one, finally, as well as replacing the elevator and rudder control rods with thicker ones. The first flight after the control linkage replacement took place on May 21, 1940. Control became rather firm and stable, but the aircraft drifted left, and in gusty winds, vibrations were felt again. 2 days later, a flight was attempted with the rudder damper removed and the throttle control system readjusted. In flight, at an altitude of about 10,000 feet, strong vibrations and nose heaviness were noted at speeds above 217 miles per hour. Therefore, the next day, the stabilizer and elevators were taped with streamers to visualize the airflow. Fuselage deformation was also monitored. This time, as well as during a repeat flight the following day, no significant vibrations were observed. On May 29th, as an experiment, the aerodynamic balance of the elevator was increased. As a result, control became much lighter, but vibrations at speeds above 168 miles per hour intensified. The next test flight with more streamers attached showed that extending the landing flaps by 15 degrees only worsened the aircraft's behavior. Only at this stage was it possible to identify the true cause of the problem. The culprit turned out to be the tailwheel fairing, which, apparently due to the turbulence of the airflow, was turning perpendicular to the direction of flight. Because of the considerable size of this component and its proximity to the stabilizer, the airflow around the elevator was disrupted. Eventually, the fairing was removed, since reinforcing the compensator, which set the tail support into a neutral position, did not fully resolve the issue. The test flight on June 4th fully confirmed the correctness of this decision. No vibrations or pitching moments, either nose down or nose up, were recorded at speeds of up to 249 miles per hour. By that time, it was already clear that the prototype would be confiscated by the Germans. At the request of the Test Division of the Imperial Ministry of Aviation, several test flights were conducted to determine flight characteristics. The climb times were measured to 6,600 feet, 6 minutes, to 13,000 feet, 12 minutes 40 seconds, to 16,400 feet, 18 minutes 20 seconds, and to 21,650 feet, 24 minutes. These were the last results obtained in the territory of the then Protectorate. The aircraft was still fitted with a new small tailwheel fairing, and on June 21, 1940, a German pilot ferried it to the Luftwaffe test range in Rechlin. No information about its further fate was received in its homeland. According to some sources, the prototype was handed over to the Klemm Company for study. For the Republic, the E-51 appeared too late. It was never delivered for testing at the Aviation Institute, never flew with a full set of equipment and armament. Its photographic equipment was also never tested, and it can be assumed that it too would not have been free of problems. The Praga E51 aircraft was a 3-seat reconnaissance and light bomber, a twin-engine mid-wing of mixed construction with a twin-boom layout. The wing was solid, entirely wooden with 2 spars. The section of the wing between the tail booms had a rectangular shape, while the outer parts were elliptical. The ailerons were of box section, their upper and lower flanges were made from several layers of spruce wood and the webs from alder plywood. The covering, with a total thickness of 1.5 millimeters, about 0.06 inches, was laid from diagonal layers of bakelized birch veneer and fastened to the spruce flanges of the ribs. Inside the central nacelle, the space between the spars was covered with veneer, forming a torsion box that housed the fuel tank. The wing profiles were developed by ČKD and were geometrically similar to the basic root profile with a relative thickness of 18%. Along the wingspan, the profile gradually thinned from 15% to 12% and further to 9% at the tips. The dihedral angle of the wing in the central section was 2.5 degrees, further increasing to 5 degrees toward the wingtips. The wing incidence angle was 2.47 degrees. The slotted ailerons had a welded frame made of strong steel tubes and were fabric covered. Each aileron was attached to the wing at 5 points with special bearings. They were designed to compensate for their weight and part of the aerodynamic load. The flaps, similar in construction to the ailerons, consisted of 4 sections, 2 on each side. The inner sections, located between the central nacelle and the tail booms, were attached at 2 points, while the outer sections, located between the tail booms and the ailerons, had 4 attachment points each. The flaps could be deflected to any angle from 0 to 60 degrees and locked in the desired position by means of a hydraulic cylinder mounted on the rear wing spar inside the central nacelle, together with a system of rods and levers. The flap control lever was located to the right of the pilot's seat. The central fuselage nacelle was structurally divided into 3 parts. The middle section contained a load-bearing frame, welded from strong steel tubes located in its lower part. Wooden frames were attached to it with fabric bands and joined together with light stringers. The entire structure was covered with specially treated alder veneer about 0.06 inches, 1.5 millimeters thick. To the middle section, where the cockpit and the wing attachment points were located, the forward part was attached at 4 points with a frame of 4 load-bearing tubes and double skinning. To this was connected a tubular frame of the glazed nose section topped with a ring of special light alloy, a kind of huge bearing with rubber balls on which the nose compartment of the aircraft rotated around its axis. A hatch in the nose opened a slot necessary for the operation of the camera. Also at 4 points, the rear part was attached to the middle section of the nacelle, with a transparent, streamlined cone forming the tail compartment of the nacelle attached to its last ring frame. Glazed like the nose with organic glass, it too could rotate around the longitudinal axis thanks to 6 guide rollers. For firing, a longitudinal hatch could be opened. The pilot and navigator bombardier entered the aircraft from above with the canopy sliding backward. A small entry hatch for the gunner, folding upward, was located at the rear of the nacelle on the upper left side. For the crew's convenience, steps were fitted on the left side of the nacelle. The tail booms also had a truss-type welded tubular structure. The forward section of each boom, connected to the wing spars, carried the main landing gear leg and the engine mount attached by pins. The rear section was given an oval cross-section with the aid of wooden frames, spruce strips laid along the tubular spar frame, and birch veneer sheathing reinforced with spruce stringers glued to it. Fairings between the booms and the wing were formed from metal. The engine cowling panels were mounted on piano hinges. The tail assembly was designed as follows. The stabilizer mounted between the tail booms and both fins were entirely wooden. The elevator suspended on 8 bearing joints, and the rudder also had predominantly wooden construction, but with spars made of steel tubing. The entire tail surface was covered with veneer. The elevator and the left rudder were equipped with trim tabs, driven by electric motors installed inside the structure. The control surfaces had both mass and aerodynamic balance and could deflect 25 degrees upward and downward, elevator, and to the same angle on either side, rudder. The deflection angles were limited by rubber buffers in the system of rods and levers. The controls could be locked by fixing the control column and rudder pedals. The aircraft was controlled by a control wheel mounted on a vertical column on the left side of the fuselage nacelle, where the pilot's cockpit was located. The rudder pedals were adjustable. The control of the flight surfaces was carried out by a system of rigid rods. The rods leading to the elevator and rudder ran through the left tail boom. The landing gear was simple. It was not retractable, with a tail support mounted in the middle of the stabilizer. The robust forks of the main landing gear struts, with a track of about 13 feet, 4 meters, were welded from steel plate and concealed hydraulic pneumatic shock absorbers. The struts were completely enclosed with sheet metal fairings, which also formed the elegant aerodynamic wheel spats. The main wheels measured approximately 31 by 10.6 inches, 790 by 270 millimeters. They were fitted with pneumatic brakes operated by a lever on the left side of the pilot's seat, and could be differentiated by deflecting the rudder pedals. The tail support also had a hydraulic pneumatic shock absorber and a wheel measuring approximately 13.8 by 5.5 inches, 350 by 140 millimeters. When unloaded, it automatically assumed the central position. It was equipped with a metal fairing and towing lugs for attaching a cable. On the wingtips near the leading edge, mooring rings were installed. The aircraft was powered by 2 powerful 12-cylinder Walter Sagitta engines, arranged in a V configuration and air-cooled. These engines were inverted, meaning the cylinders were positioned below the crankshaft. Each engine could deliver a maximum output of 560 horsepower at 2,600 revolutions per minute, although this was a short-term setting. At an altitude of 15,000 feet, the engines operated at nominal power, producing 500 horsepower. The cooling of the engines was carefully engineered. Air entered the cylinders through a central channel between them, where a special system of metal deflector plates distributed it evenly to each cylinder. The airflow passed over the cylinder heads and exited through a rear slot in the engine cowling. Each engine was about 6.4 feet long and weighed 903 pounds without fuel and oil. The engines drove 3-bladed French-built propellers with a diameter of 8.7 feet. The propellers rotated leftward, and their blades were made of duralumin, a strong, lightweight aluminum alloy. The blade pitch could be adjusted, but only on the ground, not in flight. The engines were connected to the propellers via planetary gearboxes with a ratio of 3.2, meaning the propeller rotated slower than the engine itself. At the rear of each engine was a Walter centrifugal compressor, which supplied pressurized air for high-altitude operation. The carburetor had an automatic limiter that regulated the fuel supply depending on the pressure in the air boost system behind the compressor. The engines were separated from the wing and oil tanks by fireproof bulkheads for safety. Each engine had its own oil tank with a capacity of 7.1 gallons and oil level indicators. The tanks were equipped with 550-watt electric heaters to keep the oil fluid in cold weather. Oil radiators with temperature regulators were located in separate ducts under the engines. On the ground, the engines were started with compressed air from an external source, and in flight, if necessary, a special onboard compressed air cylinder could be used. Throttle control was initially operated by a hydraulic system, later replaced by a mechanical one. The throttle levers were placed to the left of the pilot. The aircraft could carry 183 gallons of fuel, weighing 1,195 pounds. The fuel was stored in 3 aluminum tanks. One central tank of 62 gallons was located in the fuselage between the wing spars, and 2 wing root tanks of 61 gallons each. All tanks were interconnected by pipelines. A reconnaissance modification with extended range was planned, which would have included an additional 69-gallon fuselage tank above the wing spars. Fuel levels were displayed on electric gauges. The fuel pipes were of high quality, while the oil lines were made of copper tubing. Each engine was equipped with a fire extinguisher that the pilot could activate remotely. Additionally, the navigator had access to a portable fire extinguisher. The main sources of onboard electrical power were two 400-watt generators, each driven by the engines via flexible shafts. The generators produced 12 volts. In addition, the aircraft carried a 20 amp-hour battery. The electrical system included a high-voltage converter rated at 1,000 volts and was divided into several independent circuits. One line supplied power to the radio station installed in the nose section of the aircraft. The radio was operated by the navigator and had an external antenna that extended under the fuselage, as well as two telegraph keys for transmitting messages in Morse code. The same line also powered the crew's intercom telephone and the signal lamps of 3 colors, green, white, and red, for each crew member. Another line powered the cockpit lighting, the aircraft navigation lights, a spotlight under the nose section, and 2 landing lights on the left wing. A separate heating line provided warming for the engine oil, breathing devices for high-altitude operation, the crew's clothing, and the machine guns to prevent them from freezing. Other equipment was also powered by the electrical network, primarily an automatic camera, supplemented with a drift indicator and a device for calculating intervals between photographs. The camera itself was mounted on a special gimbal in the nose of the aircraft with a container for film located nearby. With this camera, the navigator could, by opening a hatch in the underside, take vertical photographs or angled shots in 3 overlapping rows. The instrument for measuring overlap was mounted to the right of the navigator's compass and could be removed. The hydraulic system powered the landing flaps and the throttle control of the engines. Oil pressure in the system was maintained by a pump mounted on the right engine. The pneumatic system was used for bomb release, operation of the brakes, and emergency in-flight engine starts. A 1.3-gallon compressed air tank was used for bomb release and braking, while a larger 3.2-gallon tank was used for starting the engines. A compressor mounted on the engine maintained a pressure of 362 pounds per square inch in the tanks. The instrumentation was standard for that time and included devices both for the pilot's cockpit and the navigator's station. In front of the pilot were the flight control instruments, a compass, a Sperry artificial horizon showing the aircraft's position relative to the horizon, a gyromagnetic compass, a turn indicator, an airspeed indicator with an electrically heated pitot tube, and an altimeter with 2 pointers. To monitor engine and system performance, there were 2 remote electrical tachometers showing engine revolutions, 2 compressor pressure gauges, an oil temperature indicator, and an oil pressure gauge with 2 needles for both engines. There was also a fuel pressure gauge, electrical fuel gauges for each tank separately, a brake system pressure gauge, and indicators for longitudinal trim, pitch, and directional trim, yaw. The starting magneto was shielded to reduce radio interference, and the switch had 2 channels. The navigator had his own compass, an altimeter with 2 pointers, and an airspeed indicator. The workstation of each crew member was equipped with an oxygen device with a 0.5-gallon bottle for breathing at high altitudes. Due to lack of space, the navigator's bottle was suspended horizontally rather than vertically. Naturally, parachutes were provided for crew rescue. The pilot's seat was adapted for a backpack parachute, which was always kept attached to it. The navigator and gunner put on their backpack parachutes only in dangerous situations. Under normal conditions, their parachutes hung on straps with simple clasps on the cabin wall. The gunner could leave the aircraft by jettisoning the rotating cone of the gun turret. This required removing one of the guide rollers. The aircraft was armed with 2 machine guns and could carry bombs. The first machine gun, controlled by the pilot, was fixed in the left wing near the cockpit. It was mounted so that the bullets passed outside the propeller arc to avoid damage. The pilot fired with a trigger mounted on the control column and aimed through a special circular sight in front of the windshield. The ammunition load consisted of 300 rounds with empty casings ejected through openings in the underside of the wing. The second machine gun was intended for the gunner and was mounted on a movable mount inside a transparent rotating turret in the rear section of the cabin. The gunner could rotate it a full 360 degrees, and ammunition was stored in 9 circular drums of 60 rounds each. This was more convenient than a standard belt feed. It was also planned to install a third machine gun in the right wing, where a mounting position had already been prepared. There was even consideration of fitting a 20mm cannon under the central fuselage, ahead of the bomb bay. Under the wings, in 2 rows, were racks for 6 light bombs weighing from 44 to 110 pounds, or for illumination bombs. In the center, under the cockpit, there was a special double rack for a single heavy bomb weighing 440 pounds, partially recessed into the fuselage. Along the bomb's entire length, inward opening doors were installed. After bomb release, these doors automatically closed, filling the freed space. Bombs were released by the navigator using the pneumatic system. If necessary, the pilot could also drop bombs using a mechanical system. The navigator carried a signal pistol for launching flares. A box with 26 flares was located on the left cabin wall, and the firing port was in the floor to the right. The upper surfaces and sides of the aircraft were left unpainted, showing the dark brown color of the special treated plywood, with filled-in repair patches clearly visible. The lower surfaces were painted light blue. National markings were applied in the standard positions. The entire aircraft showed traces of numerous modifications and improvements. Metal panels and covers were painted olive green,